Challenge and Context: Common Principles and Concepts of Smart Grids. In this video, we'll talk about common principles and concepts of smart grids. At the end of this video, you will be able to comprehend the deployment of energy management systems, name various flexibility options and understand their role in a smart grid. Renewable energy sources, especially photovoltaic and wind generation, are fluctuating power sources. Let's compare it with other generation types over the same day to better understand fluctuation. Nuclear power shows few fluctuations. It works at its optimal production day and night. It's easy to forecast. Coal-based power generation is controlled to respond to load fluctuation. On the contrary, renewable energy is not controlled and fluctuates over the day. Comparing 2-3-day periods with each other, the difference for PV generation is highlighted. Although the curve fulfills the characteristics with the peak around midday and naturally no PV generation during night, the amplitude highly differentiates. For the wind generation, no characteristic curves can be observed, but the power output is fluctuating throughout the day and varies in its amplitude. Forecasting of both PV and wind generation is only possible to a certain extent, and thus becomes a challenge for our energy system. Energy systems rely on the equilibrium between load and generation. For every instant of time, this equilibrium has to be fulfilled. The renewable power generation in Germany for a day in April is depicted in this figure. Whereas wind and PV are fluctuating throughout the day, biomass and hydro generation are constant. The latter are also constant and at the same level for a day in January. But wind and PV generation is strongly decreased. Including the load, the discrepancy between load and generation from renewable power sources becomes obvious. For April, renewables can only secure the equilibrium between noon and 6 p.m. For the other periods and for the whole day in January, energy management options should be considered. An energy management system seeks to ensure the equilibrium of load and generation at every instant of time. As a first step, information and communication technology is introduced for monitoring power flows and measuring generation and load in real time. Knowing the current state of the grid, additional measures can be taken to ensure the equilibrium between load and generation. On that account, the paradigm of supply follows demand has to change to demand follows supply. Previously, conventional power plants adjusted their output according to the load. With fluctuating renewable sources, flexibility options on the demand and load side are necessary. Small-scale flexibility options start at household level. Energy storages can capture energy at a certain time, keep it, return it at a later time, and therefore help to secure the equilibrium between load and generation. One specific example is an electric car. By charging the battery in time intervals of relatively high renewable power generation, it supports the balancing between generation and load. This approach of active user participation can also be applied to other energy-consuming tasks that can be shifted time-wise. A washing machine might be such a task. Energy price incentives motivate to shift the washing process to time intervals of relatively high renewable power generation. All these options require awareness of the importance of consumer flexibility and active user participation. Flexibility possibilities on a bigger scale include virtual power plants and multi-energy systems. A virtual power plant serves as an aggregator of distributed energy resources, including renewable generation from wind and PV, storage options and electric vehicles, and other controllable loads. It aims at enhancing the generation and retail of electric energy and thereby offers flexibility potential. A virtual power plant monitors and controls its resources and loads according to contracts. The contracts with the distributed generators and the storage units cover the availability of the resource according to season and time of day, as well as the general energy and power controllability of the units. The contracts with the controllable loads may cover the availability of the loads based on location or time of day and the comfort level of each consumer. Comfort levels are, for instance, the upper and lower temperature limits of thermostatically controlled loads, defined by the consumer. A multi-energy system can also enhance the integration of volatile renewable generation. It benefits from available flexibility in networks of other energy carriers. The networks are connected by power conversion units. One example are storage units that can also be implemented in heating and cooling networks. Virtual power plants and multi-energy systems increase flexibility potentials and help to ensure the equilibrium between generation and load. More insight into the operating principle of smart grids and their elements can be gained using the Smart.Grid app. 5 levels introduce generation elements, flexibility and storage options, and lead to the energy management system. By solving quizzes and interactive games, the user actively participates and acts as the energy manager in the end. They have to ensure the equilibrium between generation and load. Through a scoring and ranking system, the user can compare their own performance to others. The Smart.Grid app is available in Apple's App Store and Google Play Store. Thanks for watching.